All right, and here's where we are. We've still got 3 people here. Hopefully some more will join us. And we'll go from the current slide. If any of you are in contact with any of the other students, if you have any way to get in touch with them, I've tried emailing and the messaging and announcing and stuff like this, and so far I can't get a response from, well, that's not quite true. David sends me work in his other class, but he very seldom can come to the class, it seems like, and it's very seldom, and he hasn't been to this one, so I don't know. He may have technology issues, I don't know. But somehow he's getting me his work, so, and he's sending that somehow that way, usually through email, I think, yeah, through email. So he must be following somewhat. All right, any questions before we get going today? Oh, this is not the slide we're on, is it? Okay, the 2 of you were here last time. Were we on example 4 on page 375? Is that where we stopped? Say that again. Oh, is that where we ended? Okay. Did we get all those vocabularies done?
I think we stopped at 3 because your internet cut out or something.
Okay. So let's pick up there. Okay, we'll just start over there. On page 370, section 5.3, when solving a trigonometric equation, the preliminary goal is to blank the trigonometric function on one side of the equation. I'm pretty sure we did that one. You remember what that blank was? Isolate. Excellent. Number 2. The blank solution of the equation 2 sine theta plus 1 equals 0 is theta is equal to 7/6 pi plus 2n pi, and theta is equal to 11/6 pi plus 2n pi. What do we call it when we put every possible solution like that? Back on the very first page of 5.3, which I think is 362, it's the thing in the first red letter you see about middle of the page, the general solution. Okay, it's called the general solution. Every possible value in all of creation, of that solution, of that trig equation, those would be it. That's covered in every one of them. Okay, then number 3, I think maybe this is where we left off, or maybe not. The equation 2 tangent squared x minus 3 tangent x plus 1 equals 0 is a trigonometric equation of the blank type. Quadratic type, perfect, okay, because it's a quadratic equation. But it's quadratic in the trig function, not in the variable x. So it's a trigonometric equation of the quadratic type. Number 4, a solution of an equation that does not, I thought we did this one too, does not satisfy the original solution is an blank solution. And I told you this is where it frequently comes up when you've squared both sides of an equation. And that would have been on page 366, right at the bottom of the page. It may be earlier in the page too, but I know it's at the bottom. And it's at the very top of the page too. It says that procedure can introduce blank solutions. They're not really solutions, they are extraneous solutions. They look like they're a solution, but they really are not. So that's the 4th one there. All right, and I made all the assignments, didn't I, or did I?
I don't think so.
Okay, assignments were basically not all the odds. Any of the odds 5 through 9, they're all at Calc Chat. Any of the odds 11 through 27, they're all at Calc Chat. The 13's at Calc View. Any of the odds 29 to 37, they're all at Calc Chat. 29's at Calc View. Any of the odds 39 to 45, they're all at Calc Chat. 39's at Calc View. 47's at Calc Chat. Any of the odds 49 to 57, all at Calc Chat. Any of the odds 59 to 69, all at Calc Chat, with 61 at Calc View. 71 or 73 or both, they're both at Calc Chat. 73 is at Calc View. 75 or 77, they're both at Calc Chat. Any of the odds 79 to 83, all at Calc Chat. 85 is at Calc Chat. And then 87 is at Calc Chat. 89 is at Calc Chat. And 91 and through 95 are all applied problems. They should be at Calc Chat. 97 should be at Calc Chat. 99 is a true-false. It should be at Calc Chat. You can think about doing 101 if you'd like, and 103 if you'd like. All right, so that finishes 5.3. And we didn't get started on 5.4. That's right, I see that. I had a mark, but that was left over from a previous term. I didn't notice it when I put my paper in place. So let's get going on 5.4. Any questions on 5.3 before we leave it? Thomas, were you able to see everything you needed on the YouTube video?
Yes, sir. I believe
Okay.
so.
All right, good deal. So let's get started on 5.4. Chapter 5 is still analytic trigonometry. 5.4 is sum and difference formulas. Now, what? Have we gone a couple of sections without having any new identities? I know y'all are missing your identities. In this section, we're going to fill that wish, and you're going to have some more identities to look at. And here's what some of them are. Here's our objective. And I've got Thomas is sitting right in the wording, so I got to move you out of the way, Thomas. Get out of the way. Okay, there you are. All right. The objective here is to use the sum and difference formulas to evaluate trigonometric functions, verify identities, there's some more of those, gray, and solve some trigonometric equations. Okay? So here, we'll be using the sum and difference formulas. Now, what do we mean by sum and difference formulas? Later, we're going to have some other sums and differences, but that's a little bit different from these. Here's what we mean here. If you're taking the sine or the cosine or the tangent of not just a value, an angle, but the sum or the difference of two different values or angles. So in this section, you will study the use of several trigonometric identities and formulas, and here they are. The sine of u plus v, the sine of u minus v, the cosine of u plus v, the cosine of u minus v, the tangent of u plus v, and the tangent of u minus v. Now you might think, oh, are these 6 things to memorize? Not really, because I'll show you sort of an easy way to do it. I hate memorizing, so I don't memorize, okay? So the sine, you just have to pick up the pattern is basically what I think of, picking up the pattern. And here's what it is for sine of u plus v. Sine u, cosine u, and then the same sign here, SIGN sign, plus cosine u sine v. Okay? So it's the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. Okay. Okay, that sounds sort of reasonable. We sure don't want to have to prove that. I've had some text that goes through a proof of it, and it's a miserable experience. But just sort of remember that. That is probably worth remembering. Now, the second one, do you have to remember that? No, just if you remember the first one, it's kind of like, how do you shoot a blue elephant? Well, you may not want to shoot a blue elephant, but if you did, you'd probably use a blue elephant gun, wouldn't you? Make sense? Well, how would you shoot a red elephant? Any ideas? You don't like to shoot red elephants, huh? Well, you don't buy a new gun. You just swing him around by his trunk until he turns blue, and then use the gun you already have, the blue elephant gun, okay? Now, same thing here. Don't memorize a new formula. You don't need one. You just adapt the one you already know. Because it's sine u, you see the u hasn't changed. U is still u, okay? So the sine u's always show up as sine u's. Okay? Cosine u's show up as cosine u's. Nothing changed there with u. The only thing that changed here is the SIGN sign of v. Well, here's where your v shows up. Cosine, now it would be of negative v. But remember, cosine is an even function, so cosine of negative v is the same as cosine v, so that didn't change. But sine of v, or sine of negative v now, that is an odd function, so that becomes negative sine v. So you just have that one sign change because of the odd nature of the sine function. Okay? So you just have a sign change, and that's pretty easy. So let's do the sum for cosine. Cosine u plus v is cosine u cosine v, but with cosine things are different. It's the minus sine u sine v. Okay? That you just have to remember. Okay? Cosine u cosine v minus sine u sine v. That's the sum. For the difference, we do the same thing as before. The cosine of negative v doesn't change because it's an even function, but sine of negative v changes its SIGN sign, so that makes that a plus. The u's stayed just like they were. Okay? So you just change the sign again, but now it goes from, rather than plus to minus in sine u, it's minus the plus with cosine, plus sum and difference formulas. Now, the tangent of u plus v. This looks a bit bizarre, but what you could do is just take the ratio of sine u plus v to cosine u plus v. But that is a mess. So it's probably easier just to go on and get the formula. So it's tangent u plus tangent v. That almost follows exactly from what you would expect. But now you divide it by 1 minus the product of tangent u times tangent v. Okay? Plus in the numerator, minus in the denominator. Well, if you go to u minus v, remember tangent is also an odd function, so the tangent u, since the u didn't change, that stays the same. But because you're doing now a minus v here, that becomes a minus tan v there. And because it changed that tan v sign here, you also change it there. So now it's a plus, minus in the numerator, plus in the denominator. Tangent u minus tangent v over 1 plus tangent u tangent v. Now, do I memorize these? I said I don't like memorizing, so frankly, no, I don't. If I ever need it, especially that tangent one, and very seldom do you need it, but if you ever need it, look it up, okay? If you do want to memorize it or write it down somewhere, but then go and look it up, okay? Now, what we're going to do is show how the sum and difference formulas can enable you to find exact values of trigonometric functions, not approximate values, exact ones involving sum and difference of your very special favorite angles, okay? So, and that's going to be one use of the sum and difference formulas, being able to evaluate some angles exactly that you wouldn't have been able to do otherwise. So here's example 1. Find the exact value of sine of pi 12ths. Now, you could plug it into a calculator and you'll get an approximate value. It may be good for 9 digits or so, but it's still an approximate value. Okay? To get an exact value, remember those favorite angles that we used to have, and we still have them. Remember what they were? Certainly one is 0. What's the next one? Pi 6, pi 4ths, pi 3rds, and pi halves. We know the sine of all those. We know the cosine of all those. We can calculate the tangent of all those. Those are our favorite angles of all time because we already know their exact values. Anything else, sine of pi 5ths, you're going to have to use a calculator, okay? But can you come up with some combination of these either adding or subtraction, that comes up to be pi twelfths. And since pi twelfths is less than any of these except 0, it's going to have to be a difference. So what I suggest, these that you know and love to have, let's write them all in terms of twelfths. This will be 0 twelfths. This will be 2 pi twelfths, right? What would that be? Pi fourths is how many twelfths? 3 pi twelfths. Pi thirds will be how many twelfths? 4 pi twelfths. Y'all are answering so well. And pi halves will be how many twelfths? 6 pi twelfths. Right? Now that you've got the same denominators we had there, those are the same angles as these here, they're just written in twelfths. Can you see either a sum or a difference that may come out being pi twelfths? There's actually 2 of them. Please, can't somebody see? A difference between 2 of these that comes out to be only pi twelfths. I see 2. Yeah, pi fourths minus pi 6. That would be pi twelfths, right? 3 pi twelfths minus 2 pi twelfths is 1 pi twelfths. So that's the same as sine of, what do we say? Pi fourths minus pi 6. Agreed? And that's a difference formula. And from the previous slide, same page if you're in your book, you can write down what that is. That's sine of pi fourths times the cosine of pi 6, right? Minus sine, the sines are, SIG and sines are the same, and that would be minus cosine pi fourths times the sine of pi 6. And it is a minus sign because the sine of minus pi 6 is minus sine pi 6. Okay. Now, here's what I was afraid of. Does anyone remember what the sine of pi fourths is? These were our favorite angles. You knew and loved them. Can you remember what sine of pi fourths was? Anybody? Okay. Now, I thought I had given y'all the easy way to remember these, or one easy way to remember. Do a circle. Now, this happens to be a 2 circle, not a unit circle. I didn't even draw it very well. So I'm going to try to be, this is pi 6. This is pi fourths. That's not quite right, but we'll assume that's pi fourths. This one will be pi thirds. And this will be pi halves. Now, of course, this is 0. Okay? The sine of these, this is the square root of 0 over 2. That's just 0. Okay? This one's the square root of 1 over 2, which is 1/2. This is the square root of 2 over 2, which of course is square root of 2 over 2. This one is the square root of, this is the sines that I'm doing here, sines, S-I-G-N, of these angles. That's square root of 3 over 2. And this one up here is the square root of 4 over 2. But of course the square root of 4 is 2, and 2 over 2 is 1. So that's 1. Okay? So, to me, that's a pretty easy way to remember the sines of these, our favorite angles of all time. Okay? And we're looking for sine of pi fourths, and that's root 2 over 2. Y'all knew that, didn't you? Please say yes. Okay? And that's going to be multiplied by the cosine of pi 6. Well, to get cosines, you go in the opposite direction. Cosine of pi halves is 0. Cosine of pi thirds is root 1 over 2, which is 1/2. Cosine of pi fourths is the same. It's root 2 over 2. And cosine of these are the, I should have written, okay. I'm going to do these are the signs here, okay? Give me your favorite color of those listed here. Give me a color. Purple, okay? I like purple too, okay? The cosine will be purple, and that would be 0, which is square root of 0 over 2, which is 0. This is the square root of 1 over 2, which is 1/2. Now you can't read my writing. This is the square root of 2 over 2. This is the square root of 3 over 2. And this is the square root of 4 over 2, which of course is 1. Those are your cosines. So cosine of pi 6 is, I'll go back to dark now, okay, is the square root of 3 over 2. Right? Cosine of pi 6, right there. Minus, what's cosine of pi fourths? Square root of 2 over 2 times square root of pi, sine of pi 6 is sine of pi 6. Is someone talking to me? Okay, I guess not. Okay. What is sine of pi 6? Second one we did. It's 1/2. See? Sine of pi 6 is 1/2. Okay? So, let's continue. Multiply these two together, and you get square root of 6 over 4. Multiply those two together, and you get the square root of 2 over 4. So this gives you as an exact answer the square root of 6 minus the square root of 2 over 4. You don't need the parentheses there. I'll put them for effect. All right? Does that make sense?
Yes.
All right. Let's see how they did it. They probably didn't go into as much detail as I did. But please, folks, these things that are the fairly simple angles, the ones we use a lot, get to know them. Get to know their trig functions, okay? Use them enough. That's how I got to know them. I use them frequently enough that, of course, I use them more than you ever will because I teach it. But let's see how they proceed. Okay? To find the exact value of sine of pi 12ths, we use the fact, and they use the different one. Remember, the ones we had, I used pi fourths minus pi 6. But that other one, pi thirds, was 4/12 pi, and pi fourths was 3/12 pi. The difference of those is also 1/12 pi. So they're going to use a different one. Huh! They'll probably get a different answer, right? They better not. Let's see. So consequently, the formula for sine u minus v, which is pi 12ths being pi thirds minus pi fourths, sine of pi thirds minus pi fourths would be the sine of pi thirds times the cosine of pi fourths minus the cosine of pi thirds times the sine of pi fourths. So these are different angles. Let's see what they come up with. You tell me, what is the sine of pi thirds? I've already erased it, but you should know it. What is it? Help me somebody. Square root of 3 over 2. Cosine of pi fourths is square root of 2 over 2 minus, what's the cosine of pi thirds? A little louder. No, that's sine of pi thirds. Cosine of pi thirds is 1/2. Times, what's sine of pi fourths? Square root of 2 over 2. And when you multiply these two together, you get square root of 6 over 4 minus the square root of 2 over 4, which is the square root of 6 minus the square root of 2 all divided by 4. Exactly what we got before. Okay? So it didn't matter which two of those you chose. As long as the difference was pi 12ths, it still works. Okay? So let me erase this. Do y'all need it any longer? Okay. Erase that, and let's see how they proceed. Yep, that's what they did. Square root of 3 over 2 times square root of 2 over 2 minus 1/2 times the square root of 2 over 2 came up being square root of 6 minus square root of 2 divided by 4. It said try checking that result on your calculator. You'll see that sine of pi 12ths, if you do it on your calculator, it gives you an irrational number, but the first 3 digits are rounded would be 0.259. And if you do this answer here, square root of 6 minus the square root of 2, hit an equal sign, then divide that by 4, you'll get precisely the same answer. Good to at least 9 decimal places, you know. It's good forever. You just don't see it. Your calculator may round differently, but they'll be exactly the same. Does that make sense?
Yes.
Now, what difference does it make that this is an exact answer and that's an approximate answer? It really doesn't in real life, but this is the way you do it, and it's not a bad exercise, mental exercise, a exercise in trick. Okay. After every example, you have a checkpoint. Please do the checkpoints. Pretty straightforward, very similar. So let's see about example 2. Whoa, look at that. They went straight to example 5. So let's back off and let us do example 2. All right. Find the exact value of cosine of 75 degrees. Cosine of 75 degrees. Well, now they pulled one on us, didn't they? They use 75 degrees. They're not using radians anymore. Okay? Well, let's go over just like we did before, and let's do our favorite degrees. That was 0 degrees. That was always easy, or usually. Then we had 30 degrees. That was your pi 6. 45 degrees was your pi 4ths. 60 degrees was your pi 3rds, and 90 degrees is your pi halves. Okay? Now, we need 2 of these that either add or subtract to be 75. Do you see any potential takers here? Any 2? Say again? 30 and 45 add to be 75. You got it. So this will be the same as cosine of 30 degrees plus 45 degrees, because 35 plus 40, 30 plus 45 is 75. So all we need now is for you to tell me what the cosine of a sum formula is. Remember what it is? Cosine, the first one, 30, times cosine. Sine goes sine, cosine, sine, cosine, or cosine, sine. Cosine sum or difference is cosine, cosine, sine, sine. So this is cosine 30, cosine 45 degrees. But for cosine, the sum here gives you a difference there. Okay? Was that something to me? I guess not. Okay? So that's going to be minus sine 30 degrees times sine 45 degrees. Okay, now you, whoops, get out of there. Okay. Now, this requires you to remember what cosine of 30 was. Anyone remember? Square root of 30, the cosine of 30. Remember, the sines will increase going up, the cosines increase going down. So what was the cosine 30? Anyone remember? Anybody? Cosine started at 0 here, 1/2 root. Anyone got it? 0, 1/2, square root of 2 over 3. This is your 30 degrees down here. Square root of 3 over 2. I said 3. Square root of 3 over 2. Okay. I don't think she knows her microphone's on. Do you think? Okay. I don't know how I can tell her it is. She may have me muted, but not herself. Okay. What's cosine of 45? Anyone know? Help me, somebody. Cosine of 45. Come on. What was the one in the middle? Both for sine and cosine. It was exactly the same. Square root of 2 over 2. Perfect. Okay. Minus, what's the sine of 30? The one at the bottom here, just moving up, is what? 1/2, 1 over 2. And, now the pen starts doing that, I think, sometimes when the internet signal goes weak. And it must be going weak on me. Okay, there. And what's the sine of 45? Square root of 2 over 2. Perfect. And then when you multiply these out, again, you get square root of 6 over 4 minus square root of 2 over 4, which is exactly the same answer we had before. Root 6 minus root 2 over 4. How can that be? Well, here's how it can be. The earlier one was sine of pi 12ths. Okay? What is the angle in degrees for pi 12ths? It's exactly half of pi 6, and pi 6 was 30 degrees, so this is the same as sine of 15 degrees. Half of 30 is 15. Okay? Now, what's the relationship between 75 and 15? Do you see one? What happens if you add them together? What do you get? 75 plus 15 is 90. Anytime you have two angles whose sum is 90 degrees or pi halves, then you have complementary angles, right? And the sine of an angle is the same as the cosine of its complement. And the cosine of a complement is the same as the sine of the angle. Okay, or the cosine of an angle is the same as the sine of a complement. So that's why they're the same answers, because you're dealing with the same, basically the same trig functions, because they're co-functions of complementary angles, and they are the same. So no surprise there. Okay? That doesn't mean all these combinations will turn out that way, but these two just happen to do that. Now, example 3, they also skipped. So any questions on this one? Should I erase it, or you want me to leave it up a little longer? Let me know. Okay. All ready to erase. All right. Now, let's do example 3. Find the exact value of sine of u plus v. That's very much like what we had on across the page there. Given that the sine of u is equal to 4/5. Okay? Where 0 is less than u is less than pi halves. Okay? And, giving you lots of hints here and clues, cosine of v is equal to minus 12/13, where, last clue, pi halves is less than v is less than pi. Wow. A lot of hints there. So let's find the exact value of that expression. Now, before we do, I want to ask you, what is this telling you about you? This term right here, this expression here, 0 less than u is less than pi halves. State that in another way. Where does u live?
It's in between 0 and pi halves.
Is
0 degrees and 90 degrees.
Okay, did you say in the first quadrant? Say yes. Yeah. Okay, yeah, that's right. It's in the first quadrant. Anything between 0 and pi halves, you're in the first quadrant. Okay? Now, is the sign of an angle in the first quadrant positive?
Yes.
Yes. Any trig function in the first quadrant is positive, so that makes sense. Now, what does this tell you about v? Where does v live?
In the third quadrant.
Not third, second. Pi halves to pi, that's the second quadrant, right? Now, is cosine negative in the second quadrant? What's the answer? Yes, of course it is. Cosine, if you remember the little acrostic or acronym or whatever you call it, all students take calculus, okay, or chemistry or all state technical college, however you want to say that. All the trig functions are positive in the first quadrant. State or science or students or whatever, that takes in the second quadrant, that means only sines and cosecants, its reciprocal, are positive in the second quadrant. So that means cosine is negative there. In the third quadrant, that's between pi and 3/2 pi, then tangent and its reciprocal, cotangent, they're positive there, everything else is negative. And then in the fourth quadrant, calculus, chemistry, college, whatever that fourth one was, that's going to be cosine and its reciprocal, which is secant. Those are the only positive ones in the fourth quadrant, which means everything else is negative there. So, our problem is well posed here, that you got in the first quadrant, sine is positive, second quadrant, cosine is negative. So we can go from here, and then you tell me what your sum angle formula is for the sine. Sine of u plus v is the same as sine. Just look across the page if you need to. Sine u, help me, cosine v plus or minus, plus cosine u sine v. Okay? Now, we already know what sine u is. That's 4/5. And we already know what cosine v is. That's minus 12/13. We know what a plus sign is. There's a plus. Uh-oh. Do we know what cosine u is? Well, in this case, I would go to a circle. Not necessarily the unit circle. I'm going to make this a 5 circle because the radius down here is 5. So this is 5, this is 5, this is minus 5, and this is minus 5. I have it written all right, but that's 5. The radius is 5. Now, what is the sign in terms of x, y, and r? We know the r is 5. Okay, and it's always plus, by the way, so I won't even put minuses there. Okay, the radius is always positive, it's 5. What is sine in terms of x, y, and r? One of those identities, nice to know. How about some old hen? What was it in that way of expressing it? Sine is opposite over hypotenuse. Where hypotenuse is the radius, it's always positive. So the sine is the opposite side is the y. Because if you draw the triangle here, the opposite side is y, the adjacent side is x. So this is x, y, and r. So sine is y over r. So that means your y is 4, your r is 5. What does that make x to be? There you can use good old Pythagorean theorem. Remember what it says? Come on. X squared plus y squared equal r squared. Square of the a squared plus b squared equals c squared. A is x, b is y, c is hypotenuse. C is r. Okay? So this tells us that x squared plus y squared, that's 16, is equal to r squared, which is 25. That means x squared is equal to 25 minus 16, which is 9. So what would x be? It would be, you happen to be right here, 3. Because you're in the first quadrant, so x is equal to 3. Positive in the first quadrant. So, if you know that, cosine is what? If sine is x is y over r, what is cosine? U. Cosine u is, and remember that? Sine is y over r, what is cosine? That's called another hen, that's the adjacent side, which in this case is your x. So it's x over r. And what's your x? 3, and your r is 5. So that's 3/5 is cosine u. Okay. Now sine of v. Okay. Yo. We're over here at v. Let's do v in a different color. You want to go back to purple or a different one?
Okay, sure.
Say again?
I say sure.
Okay, purple. We'll stay with purple. Okay. Now here we have cosine x is minus 12. Now I'm going to pretend I have a 13 circle here, not a 5 circle, so I don't have to draw another one. So the radius is 13, and the x value is minus 12. So that's going to be somewhere out here. So this angle is this one right here. X equal minus 12, and r equal 13. What does that make your y? Well, it seems like Pythagoras may be a help here again, wouldn't it? You have that minus 12 squared plus y squared is equal to 13 squared. Would you agree or not?
Yes.
Okay. And minus 12 squared, I'm pretty sure, is 144. Plus y squared, we don't know, that's what we're looking for, is equal to 13 squared, I think is 169, but y'all check me on that, right? I know it's right. Then if you subtract, y squared would be, yeah, she still doesn't realize, y squared would be 169 minus 144 is 25. So what would y be?
5.
And you're right again that you choose the positive because you're in the second quadrant. And y is positive there. So y is equal to 5. So let me go back to my dark color. And we know that sine is y over r, which would be 5 over, and your radius was 13. Okay. Feel like a dentist here pulling teeth, but that's okay. So, negative, positive times negative is negative, and the numerator is going to be 48, right? And the denominator is going to be 65. Is that right? don't know where my pen went, 65, plus, this pen is slowing down, which I think means my internet connection is weakening, okay? Sorry about that. Hopefully it won't go out. Your numerator here is 15, and your denominator here is 65 again. That's convenient. Okay? Now, subtract those two, and we get minus 33 over 65. Does that sort of make sense? Okay? We're looking at the sign of the sum of these two angles. Well, the sum of this angle, that's a pretty large angle there, plus this angle here, which is quite large. This angle is going to add to this one, so that's going to put you somewhere down here in the third quadrant. Is the sign in the third quadrant negative? Yes, it is. All students take chemistry. Sign is negative in the third quadrant. Or all take technical, all students take calculus. Whatever you want to say. It's negative in the third quadrant. And it's not too far. I drew it probably too big. It's not too far from 1/2. So it's going to be something over there. This angle added to that angle. It's going to be somewhere down there. Not too far from 1/2. It's not exactly 1/2, but I get negative 33/65. Let's see what they got. This was what? Example 3. Negative 33/65. Yes, we got it. Does that make sense?
Yes.
All right. Do you need it up there a little longer? Now you see, you use every tool in your belt here to solve these problems. Pythagorean theorem, the signs of in your quadrants, your angles you know, angles you don't know, okay? Whatever it takes, as long as it's correct, use it, okay? All right to erase? Okay, let's move to example 4. Okay, example 4 says, oh boy, look at this one. Write the cosine of the arctangent 1 plus arctangent x as an algebraic expression. Whoa! Wait a minute here. Can you even do this? What do you take a cosine of, or take any trig function of? You take them of angles, right? What is an arctangent anyway? Give me an equivalent expression to arctangent 1. Okay. I'm going to do a giveaway here and say this is an angle. You want to just call it theta because that's my favorite angle? So if arctangent 1 is equal to theta, can you give me another equation, expression just like that, says the same thing, not just like this, says the same thing as that? And that's supposed to be a theta. Somehow it came out a phi or a 0 or something. That was pretty sloppy on my part. That is that angle theta. Can someone give me a formula, an equation, that means the same thing as that, but just written slightly differently? Okay. I guess she is in trig class. It sure doesn't sound like it, though, does it? Okay. Give me another expression that means the same thing. This says that the angle whose tangent, the tangent of some angle is equal to 1. So that means that the tangent of theta is equal to 1. That means the same thing, right? Is that what you understand that, right? That's what arctangent means. So it is an angle, okay? And this one, the equivalent expression here would be that the tangent of x, no, the tangent of, I'm sorry, of some other angle. Now, give me a different angle name. I used theta before. Give me another one. Alpha, okay? Okay, that the tangent of alpha is equal to x, right? So basically that's saying this represents the angle alpha, that represents the angle theta, okay? Now if you had that cosine of theta plus alpha, what would that be? According to our formulas on across the page there, what would that be? Cosine theta cosine alpha minus sine theta sine alpha. Okay, that gave us that, but are we anywhere closer to reality? Well, the question I have for you here is, what angle theta gives you a tangent of 1? The tangent of what angle is equal to 1? And if you don't remember that, remember what tangent is. Tangent is sine over cosine. Remember our ratio or quotient formula. Tangent is sine over cosine. So this is saying, where is the sine exactly equal to the cosine? What angle has the same value, sine and cosine? We've already hit it today a couple of times, well, several times. Remember my little first quadrant showing? At what place was the sine equal to cosine? Not 90. Sine of 90 is 0 and cosine of 90 is 1. No, I said it backwards. Sine of 90 is 1, cosine of 90 is 0. So they're not the same at 90. There is a place they are. 45, you got it right. So that means theta is equal to 45 degrees. So let's write it that way. Cosine of, you want it degrees or radians? I don't really care. Degrees? Okay. 45 degrees plus alpha, we haven't figured out what alpha is yet, is equal to cosine of 45 degrees times cosine alpha, we don't know what that is yet, minus sine of 45 degrees times the sine of alpha. Okay? Now, that's what we've got here. That's what we're looking for. What is cosine of 45? Square root of 2 over 2 times cosine alpha minus square root of 2 over 2 times the sine of alpha. Okay, so now our problem is, what in the world is that alpha? Well, we know here that the tangent of alpha is equal to x. So let's draw our circle here. Okay? And tangent is, oh, this is bad. This is sort of bad. Let's not call this the xy axis. Let's call it the AB axis. Or let's call it, better than that, yeah, the adjacent opposite axis, the AO axis. Okay? The reason I'm doing that is we don't want to call it xy because we already have an x in the problem here, and that may not be the same as the x for the axis. So let's call that the opposite, the adjacent side is the x side, and the opposite side is the y side. Okay? And what is the tangent of alpha then? It's Tangent of alpha is, remember, taking oats away. Oats is the opposite side, so that's the y-axis here. Let's not call it y, let's call it O. So this would be opposite over adjacent. Okay? Now, your radius here is 1. Okay? So, let's just draw an angle in here, and we'll call that alpha. Okay? And the adjacent side here is x. The opposite side here is x. That's why I didn't want to call that. And the adjacent side here, the radius is 1. Adjacent side here, what would that be? Pythagorean theorem comes into play here. This says that a squared plus opposite squared, which in this case is x squared, is equal to 1 squared, which is 1. So, the a squared is equal to 1 minus x squared. So a is equal to the square root of 1 minus x squared. Okay, now we've assumed you're in the first quadrant. It's okay to do, okay? We'll just assume we're in the first quadrant. And I think we'll be safe there. So that's what your a is, okay? And remember, the sign is opposite over hypotenuse, okay? And cosine is adjacent, which is the square root of 1 minus x squared, okay? So let's write them in now. That would be, let's factor out the square root of 2 over 2. That's in both terms here. And then your cosine alpha is the square root of 1 minus x squared minus, we factored out the root 2 over 2, and sine is opposite over hypotenuse, which is just x. There we've written this thing here as a function of x. Root 2 over 2 times the square root of 1 minus x squared minus x. And why in the world did they yuck? What they did was fine, but did I do something backwards here? Yes, I did. Oh, no. Y'all let me get that far through the problem and didn't correct me? This is not an arc tangent. That was an arc cosine. Goodness gracious, folks. You let me do all that. Okay? Yuck. I wasn't paying attention. I'm sorry. This is a cosine, not arc tangent. I thought, how did they get the wrong answer? Okay. Well, you do everything we did here, only this is going to be cosine of alpha. And this made it, the whole problem, a little bit easier. Cosine of alpha is equal to x. That's what we wanted it to be. So let's get these corrected here too. Okay. This really made the whole problem easier. Okay. Because the cosine, that's your x. The adjacent is that. Your hypotenuse is still 1. That makes this the square root of 1 minus x squared. Okay. And that's what you're wanting for the sine. So I've got everything backward here, I think. Okay. Yeah, because cosine of alpha is x minus the sine of alpha is the square root of 1 minus x squared. Okay. Okay. Now, that's the answer they have in the book. But they wrote the square root of 2. They distributed that across and said square root of 2x minus the square root of... And then they put this 2 inside the radical, the square root of 2 minus 2x squared, which is right, all over 2. Just a different way to write the answer. I think mine's better or clearer, but same answer. Sorry about that. I didn't read well. And there is a checkpoint. Please do the checkpoints. All right. How are we doing on time? We're okay, aren't we? Oh, I've got my... Yeah, we got 5 minutes, right? Okay, so let's move on to example 5, and I think they have example 5 on the things. Can I go on and advance?
Yes.
Okay, so let's... Here is example 5. Use a difference formula to prove the cofunction identity. We've already used that cofunction identity once today when we had 15 degrees and 75 degrees. We did that. Let's see if that was right. We've been using it. Let's see if it's right. How does the cosine of a difference go? Remember that formula? If not, look across, well, back a page now. Back a page because you're one page back. Okay, cosine of pi halves minus x. Think of that as u minus v. You tell me. Cosine of pi halves cosine x. It doesn't change sign, remember? But the sign does, so it becomes a plus sine of pi halves times the sine of x. That changed the sign. The question is that equal to sine x? Well, you tell me. What is cosine of pi halves? Anyone remember? Cosine of pi halves. Anybody? Please. Cosine starts at 1, and at pi halves it's gone down to 0. So that's 0, which makes this whole term 0. So this is a 0 here, plus, what's sine of pi halves? Please tell me you remember that one. Help me, somebody. Remember, we're going. We went from here to here. At pi halves, it's square root of 4 over 2, which is 1. 1 times sine x, sure enough, is equal to sine x. You would have thought that would have been the hardest problem we had. That's actually the easiest. Yep, that was real easy to prove. Sine x is equal to sine x. Okay? Let me clear my scratch off the page. Do you need it any longer? Anybody? Okay. And let's see how they did it. Using the formula cosine of u minus v, you have cosine pi halves minus x is cosine pi halves cosine x, and minus a minus is plus sine pi halves sine x. Okay? Well, cosine pi halves is 0 times cosine x is still 0. Sine of pi halves is 1 times sine x is sine x. So you have 0 plus sine x is sine x, and sine x is equal to sine x. Okay, how many times can we say it? All right. There is another checkpoint. Please do the checkpoints. Okay. We got 1 minute left. Can we do example 6 in a minute? I don't think so. Okay? So we're going to begin next time with example 6. So let me mark my place here. And we almost finished 5.4. Less homework exercises here would be any of the odds, either 7 or 9. They're both at Calc Chat. They have 2 parts each. Any of the odds 11 through 25. They're all at Calc Chat. 21's at Calc View. Any of the odds 27 through 33. They're all at Calc Chat. Any of the odds 35 to 39, I think. Let me make sure I'm not going too far here. Yeah, I think we're okay. Okay. So where were we? Anywhere. I already said 35 to 39, did I? If not, 35 to 39, they're all at Calc Chat. 35's at Calc View. 41 to 45, they're all at Calc Chat. 43's at Calc View. And any of the odds, 47 to 51, they're all at Calc Chat. Okay? And we did one like 53 or 55, they're both at Calc Chat. 53's at Calc View. And then the verifying trig identity, that we just did one like that, and that was any of those 57 to 63. They're all at Calc Chat. 59's at Calc View. Stop there. We'll pick up the rest of those next time. All right. And while we're here, 2 things. One, an announcement I meant to make at the beginning. I forgot to. Student course evaluations are now open. You can go to, if you want to, just find that in your email. It should have been sent to you. And I bet you in that email they had a link. You can click on the link and you're right there at the student course evaluations. Please do those, folks. Please. This, more than just about any other term I've ever taught, really important to have these because we need to see what students are thinking, how we've been performing, how the course is going in this kind of environment. Please do the student course evaluations. Okay? And the other thing I was going to say is this class, I've only received 2 research papers out of about 11 students. That's not too good. I received most of your test 1, but I'm still missing 1, 2, 3, 4 of those. Test 2, I've only got 3 test 2s in, and test 3 will be coming when we finish 5.5, which is pretty soon. We should finish 5.4 next time and start in 5.5 and then finish 5.5 by next Thursday, which will get us the test hopefully by next Thursday. Any question?
No, sir.
All right, good deal. Hope you have a good weekend, a safe weekend. Take care, and we will be back next Tuesday. I've been recording everything. I can write on the screen. This is a good feeling to be back in the saddle again. All right, so have a good weekend.
You too.
All right, bye-bye. Any questions?
No, sir.
Okay, we'll see you then Tuesday. We'll end the meeting if there's no questions, and end it for everybody. And I need to stop the recorder.